three-phase controlled rectifiers. These are some of the basics of three-phase system. In a star-connected ABC sequence, if we take VAN as reference, the VBN will start after 120 degree. Then again after 120 degree there will be VCN. So if we represent this in this waveform, here is VAN and it is starting at time t equals 0 after 120 degree, so roughly about 6 millisecond, the VBN will start, and after again 120 degree the VCN will start. Here the total cycle is divided between 12 blocks, so each block is 30 degree apart. So in this case the gap between VAN to BN is 4 blocks and BN to CN is 4 blocks. So if we derive the equations, VAN should be the reference, hence VM sin omega t. So VBN is equal to VAN in magnitude but is displaced by 120 degree. So VBN is equal VAN and clockwise 120 degree. So a clockwise 120 degree means a negative 120 degree, so twice pi by 3. So in case of a CN, it is counterclockwise 120 degree, so a positive 120 degree. We can also derive the line voltages from this diagram. So VAB will be the summation of VAN and minus VBN. So if we extend the BN in the opposite direction, it will represent minus VBN, so the summation will indicate VAB, and the angle between VAB and VAN is 30 degree, and VAB leads VAN by 30 degree. This means VAB will start before VAN. So if we get back to our waveform, if VAN starts at t equals 0, VAB will start before VAN and the VBC will follow VAB after 4 blocks, and again after 4 blocks there will be VCA. As this is a continuous system, we will get the VBC and VCA from the previous cycle. So if we numerically calculate VAB, this will be root 3 times VM into sine omega t plus pi by 6, so omega t plus 30 degree. Since VAB is in a counterclockwise angle from VAN, so this 30 degree will be positive. So again we can calculate the value of VAC and so on. This will be very helpful when we derive the VDC and VRMS. Again, something important to note, this point is represented by this crossover point. So what is a crossover point? It is basically a point which is 30 degree after the starting point or t equals 0. As you can remember, a thyristor must be triggered to turn on. So we need to provide a gate pulse to turn on a thyristor. And the angle of gate pulse is called firing angle or alpha. But here are some controversies regarding the starting point of alpha. Let me clear this up. In our textbook and other different books, alpha is calculated from this crossover point. So in this case, alpha equal 30 degree with respect to crossover point. But the rest of the world follows this terminology. They calculate this angle from the starting point, I mean t equals 0. But in this book or in our textbook, we will follow this crossover point referencing. So to clear up, it will be mentioned whether it is with respect to crossover point or with respect to phase voltage. If it is with respect to crossover point, we have to start calculating the firing angle from this crossover point. So in this case, it is 30 degree. In case of a phase voltage reference, we need to calculate the alpha from the beginning, or t equals 0. So in this case, it is 60 degree. So here's the controversy. We are calculating alpha from this crossover point, but we are calculating these sine waves from this t equals 0 time. So in our lecture, we will follow this crossover point referencing since it is in our textbook. So why should you go for a three-phase system rather than a single-phase rectifier system? This is the output diagram of a single-phase full-wave rectifier, and this is the output diagram for a three-phase full-wave rectifier. So you can clearly see that the peak-to-peak ripple voltage is less in case of a three-phase system. In a single-phase system, the peak-to-peak ripple voltage is much higher. So the difference between the lowest portion and the highest portion of the curve is greater. So a higher value of capacitor is needed to smooth out this voltage. So in case of a three-phase, the capacitor requirement will be much smaller. And again, we are getting a higher voltage in case of a three-phase, since the three-phase voltage is √3 times the single-phase voltage. So it is always preferable to use a three-phase system if our system permits, as the energy density of three-phase system is much greater than a single-phase system. But surely this three-phase system is more complicated than a single-phase system. So in case of an industrial application, a three-phase rectifier system is always preferable. In case of household application, we usually use single-phase system. Here is a circuit diagram of three-phase half-wave converter or three-phase half-wave control rectifier. Here phase A, B and C are connected to the load through thyristor T1, T2 and T3, and the negative side of the load is connected to the neutral. So at any given point, the maximum load voltage will be the value of phase voltage. So these are the input phase voltages of a three-phase star connected ABC sequence. Since we need to consider only one cycle, you don't need to draw beyond this grid line. So you need to draw from 0 to twice pi. So VAN will start from 0. It will peak at alpha equal 90 degree or pi by 2. So 3 blocks from 0. It will have the peak value, and again after 3 blocks it will get to 0. Again after 3 blocks it will get to negative maximum, and after 3 blocks it will be 0. So here is the full waveform of VAN. So after VAN, or after 4 blocks of VAN, the VBN will start, and it will follow the same pattern as it was continued from the previous cycle. And again after 4 blocks of VBN, VCN will start, and it will follow the same pattern as well. And here is our crossover point. So if we want to solve this circuit, we must get back to the basics. So here is a diagram where the cathodes of 3 diodes are connected to a common point, which is further connected to a load, and the other terminal of load is connected to ground or 0 volt. So which diode will be forward biased? So in this case, diode D2 will be forward biased, since the maximum positive voltage is connected to its anode as compared to other diodes. So when D2 is forward biased, this node becomes 250 volt, and automatically D1 and D3 get reverse biased. So in case of a common cathode multiple diode system, the diode which has the highest voltage connected to its anode will turn on, and others will be turned off. So this analogy is useful in solving this circuit. So these thyristors are in similar situation where the common cathode terminal is connected to a lower voltage. So the thyristor which has highest anode voltage will turn on. But since these are thyristors, not diode, we have to provide a gate pulse at the right moment. So here is the possible conduction zones of these thyristors. So this T1, as it is connected to phase A, will only conduct during the positive half cycle of phase A. During the negative half cycle of VA, the T1 will be automatically off, whether the gate pulse is given or not. So same goes for T2, as the anode of T2 is connected to phase B. This T2 is forward biased during the positive half cycle of BN. And again for T3, the probable conduction zone is the positive half cycle of VCN. So here the possible conduction zones are marked in different colors. So as you can see, we are solving this circuit for a firing angle or alpha is equal 0 with respect to crossover point. Since this is the crossover point, the alpha equals 0 means the first thyristor will be triggered right at the moment of this crossover point. So if T1 is right at the crossover point, the T2 will be shifted by 120 degree, since the phase angle gap between T1 and T2 is the phase angle gap of VAN and VBN. So we will have T2 after 4 blocks. Then again after 4 blocks we will have T3, since T3 is connected to VCN, and the phase angle between VCN and BN is 120 degree or 4 blocks. So in order to draw the output wave shapes, we need to first draw the input wave shapes correctly, and then we need to follow the triggers as well. So you can see right away this T1 is triggered at this point. So before this point, T1 cannot be turned on. So after this trigger, T1 will be turned on, and if T1 is turned on, the load is directly connected to this A terminal, and the other terminal of load is connected to the neutral. So if we measure the voltage of the load, we will get VAN. So the output voltage wave shape will be similar to VAN. So this portion of VAN will be copied to the output or load. So what will happen if we trigger T2 at this point? Since the conduction zone of T2 starts from this point, the T2 is ready for turning on. But since the value of VAN is higher than VBN at this point, the T2 cannot be turned on, because we know the highest anode voltage will turn on the diode or thyristor. So in this case, if we trigger T2 at this moment, the T2 will start conducting, because at this point the value of VBN is higher than that of VAN. So if T2 turns on, then T1 will be forced to turn off by this logic. So after triggering T2, the load will be connected to point B. So the load voltage will be VBN. So we will copy the shape of VBN in this section. The same thing will happen after triggering T3. So after triggering T3, since VCN is starting to rise beyond VBN, if we trigger T3 at this point, the load will be connected to terminal C and the load voltage will be equal to VCN. So we will copy the value of VCN right in this section. And as the cycle continues, after 4 blocks or 120 degree, there will be again VAN, or this trigger for T1. So if we trigger T1 at this point, the load voltage will be similar to VAN. So this cycle will continue, and this portion of the wave shape will be continued here for the next cycle. So if we continue to solve this for alpha equal 30 degree, then the input and conduction zones will be same, but the trigger will be shifted by another 30 degree. So if we compare it with alpha equals 0, it will be shifted another 30 degree. The entire group will shift 30 degree further. So the entire group means T1, T2 and T3. So what will happen if we trigger T1 30 degree after this crossover point? So right before this point we will have 0 output, and after that point we will have VAN up until we trigger T2. Though here VAN gets below VBN, but since we are not triggering VBN in this region, the VAN will continue until T2 is triggered. So we will have VAN up until this point, and after that if we trigger T2, we will get this portion of VBN, and after T3 we will get VCN, and after that VAN will continue for the next cycle. So just a quick reminder, these triggers are separated by 120 degree, or in this case 4 blocks. So if we solve it for alpha equal 60 degree, then this whole triggering system will be shifted 30 degree further. So here is alpha equals 60 degree with respect to this crossover point. We will get VAN after this triggering, and the VAN will stop there. because after this point the value of VAN is getting negative, and a negative value of VAN will automatically turn off this T1. But again, keep that in mind, we haven't turned on this T2. T2 is turned on at this point. So there will be a gap which we are calling discontinuous conduction mode. So if we get back to our previous diagrams, the conductions or the output voltage is continuous. Here output voltage gets to 0, but immediately after that VBN starts. So there is no gap. So we are calling it continuous conduction mode. But in case of alpha equals 60 degree or alpha greater than 30 degree, we are getting into the discontinuous conduction mode. So in this case, if T2 is triggered at this point, we will get VBN again, which will go to 0 at this point since VBN becomes 0 here, and in this portion we will not get any output. So again there will be a discontinuity due to the fact that the thyristor cannot be turned on during this reverse bias or the negative cycle of VBN. So after that, or after another discontinuity, the VAN will continue for the next cycle. So if we get back to our first diagram where alpha equals 0, we can derive the formula for VDC and VRMS from this continuous conduction mode. So VDC is basically this area of the curve. Since this pattern is a repetitive pattern and this pattern is repeating after every 4 blocks or 120 degree, so this is itself a 120 degree cycle. So if we calculate the area under this VAN, we will get the value of VDC. So the formula of VDC is 1 by T. Here T is 120 degree because this pattern is repeating after every 120 degree. So the T or time period of this output wave shape will be 120 degree. So twice pi over 3 is 120 degree. So 1 by 120, and the limit will be pi by 6 to 150 degree. So in this case, as alpha equals 0, we will have pi by 6 to 5 pi by 6. So pi by 6 means 30 degree and 5 pi by 6 means 150 degree. So 30 to 150 degree. Again for VRMS, the limit stays same, just the equation of RMS will apply, and the same equations can be found in the book. So if we move on to alpha equal 30 degree, the angle will be 60 degree to 180 degree. So if we get back to our equation, this will be 30 plus 30 and 60, and 150 plus 30 equal 180. So the rest of the equation will remain same, just the limit will be changed. So if we move on to alpha equals 60 degree, the previous equation will not apply because there is a discontinuity. So in this new equation, the period stays the same, which is 4 blocks. It is 120 degree. So twice pi over 3, and the limit will be changed
to pi by 6 plus alpha to pi, because no matter what we do, this conduction won't go beyond pi. So for the case of discontinuous mode, this upper limit will be restricted to pi. These equations can be found here in the book.